The next and final part of our content is the lightning talks. And we have 3 lightning talks registered. We have Roland Haas, Yufeng Liu, and Haley McPherson. So Roland, you're up first. You can start when you're ready.
Okay, give me a second. Let me see if I can share my screen. There we go. Thanks for having me. So I think, so I thought I'd give a very quick lightning talk to give an update on this code PoweR that we had suggested to be included in the Einstein toolkit, and that there were some questions about. So I just want to give a very quick recap what it is and what it does and why we would like to include it. So PoweR stands for Python Open Source Waveform Extractor. So it's a little bit of a contrived acronym. And it's essentially a small Python script to process numerical relativity simulations. That was developed originally by students here, and I'm listing all the students that are involved in the project here. So it's about, I think, 6 students that have worked on this over the time, plus myself and Eli Huerta, who kind of provide a little bit of oversight. And it is essentially a package that's started in a while. We already had a presentation on PoweR in 2017 where Daniel Johnson, who was the first person to work on this, gave a presentation at the Einstein toolkit meeting at NCSA about what it could do at that one point. And basically at that point, PoweR, and that's still some of its basic functionality, computes the gravitational wave strain at Scri+ using the multipolar Psi4 output that's existing in the Einstein toolkit. It's a pure Python code that we wrote to have something that runs easily on clusters. It uses the fixed frequency integration method that was developed by Christian Reiswig and Dennis Polny, same way that pretty much everyone else does. And then that version used an extrapolation method to go from finite distance radii to Scri+ using just the power law decay of the wild scalars, amplitude and phase. So that's basically the peeling theorem. And it's kind of a schematic plot on the left-hand side. So if you're measuring your amplitude, say, for the wild scalar at a couple of different radii, which are these green dots, and then you can fit the power law to that, and of course you can extrapolate what it would look like at Scri+ at infinite distance. So that's the idea behind that. There is not much physics that goes into that other than the idea that there's some power law decay. So this, of course, is not new. All of this had been implemented before in Ian Hinder's excellent simulation tools, which are Mathematica based. And in fact, we compared our results against Ian's results. And the plot on the right-hand side is the plot that Daniel showed 3 years ago, showing that indeed there is no difference visible between what the results that PoweR would produce and what the simulation tools would produce for, say, one of the simulations that we did at the NCSA gravity group that had some eccentricity on it, and that's why you get these oscillations in the amplitude. So all of this seemed to work, and that's what worked 3 years ago. Now what we have in 2020 is that we extended this tool a little bit, various ways, so various student projects were involved in this. So we just made it more flexible so that it isn't tied quite so much to the way that exactly we do the simulations here. We also implemented an alternative method to extrapolate to Scri+. That's based on a post-Newtonian method developed by Hiroyuki Nakano. I'm getting his first name wrong. When he was at RIT, and that was published in 2015. And that one basically gives you a gigantic formula like the one that I'm showing here that you have to evaluate to get the value of Psi4 at infinite distance given a value of Psi4 at finite distance here. And then you have to take a couple of integrals over time, and there's also a time derivative somewhere in there. So that one has a bit more physics in there because this long equation here is effectively coming out of some post-Newtonian or self-force type or perturbation theory type calculation that lets you get an idea of what the wave would look like at infinite distance if you have an idea what it looks like at finite distance. So it's an alternative method to get it out. It's been used, as far as I know, by the Rochester group. So it is just a different way of doing the same thing. And it's always good to have 2 different methods to compare with the answers. So that's one of the new things that we have in there. The other thing that we have in there is that we extended PoweR to do more than just a gravitational wave extraction, but we wanted to integrate it with a set of scripts that actually produces the waveforms and includes in the waveform data the metadata that describes the simulation in a unified file with a well-known format. And the format that we picked for that was the LIGO numerical relativity injection waveform format that's described in a paper by Patricia Schmidt, Harald Pfeiffer, and a couple of other people, published by LIGO here, and there's also an archive paper on that. And that basically is an HDF5-based format that has all the attributes that you would like as metadata in the HDF5 file, so that you know exactly what you're dealing with, who produced the code, what's the masses, what's the mass ratio. So this is a uniform file format rather than having just a collection of text files that every group has to come up of their own. We've also added code to compute an estimate for the eccentricity that would be present in the gravitational wave. And that's something that can measure eccentricity that's finite, not just some residual eccentricity left over from a quasi-circular in-spiral, but in fact, if you have an eccentricity of 0.1 or 0.3 or so, you can still measure that and you can get some idea of what the eccentricity is. This is done by basically comparing some quantity in the numerical relativity waveform to the equivalent quantity in a post-Newtonian model based on the Enigma model that Elio Huerta here had developed. And that way you get a handle of the eccentricity that is a little bit less coordinate dependent than what you typically have. In this case now, it's something that you would correlate with a post-Newtonian idea of what eccentricity is. So it's a bit more physical and a better label for eccentricity. On the right-hand side, I'm just showing a plot of what this looks like. That's a plot that was produced by Sarah Habib, who actually implemented the method, where in orange that you can't quite see is the numerical relativity measure of the quantity. In blue is the fitted post-Newtonian answer. And then basically you take the parameters that describe that post-Newtonian waveform as the eccentricity measure that you assign to this numerical relativity waveform. Right, so that's basically it. PoweR is certainly not the only thing that can do something like that. There's other tools to do very similar things. Primary among them is the simulation tools by Ian Hinder, which can do the Psi4 to the strain computation. It can also do extrapolation, but it's unfortunately in Mathematica only, so it's always a bit tricky to get to run on clusters. There's Wolfgang Kastaun's post-cactus tools, which unfortunately can't do the extrapolation because this typically is not so important for what he's trying to do. They are in Python only, so they're much easier to use. And then finally, there's actually something in the Einstein toolkit. There's a tool called PyGW analysis by Christian Reiswig. There's a G missing here, which can do the computation of the strain from Psi4, but it doesn't do any extrapolation yet. And that works, but it's a little bit dated maybe by now. So it would be nice to have an updated thing here. So that's kind of what we looked at, and that's why we decided to have our own. And then last slide, this is the current status. So what we currently have is we have all the bits and pieces. We have the extrapolation using a power law. We have an implementation of Nakano's method implemented by Brockton Brendel, who's a student working with us. We've got the LIGO format converter that was implemented originally by Wei Ren, and then worked on somewhat later by Robert Nagel. So now we have a pure Python code that uses all the LIGO stuff that's required. We have the eccentricity estimator that Sarah Habib worked on, which currently uses some C code that Elio had written, and that then Robert translated into Python code, but it's a bit slow. Everything is available for download from here. And we have a couple of leftover work items that we need to address to make this actually feasible to include in the Einstein toolkit. We definitely need to clean up the code. We want to make the whole thing more robust so that it's less tied to a particular way of organizing your simulations. It needs some speed up because with the Python code, it tends to be too slow to really be very useful. And definitely there needs to be documentation. And that's kind of my hopefully 5 minutes overview of what PoweR can do. Any questions?
That looks like a very nice tool, Roland. I'm wondering if I have a little tool that I have for Python that may or may not help you with your speed up, or we could look at it. Basically, what it is it automatically generates an interface using PyBind 11, which is a C++ interface Python code.
No, we don't want that.
Well, let me finish.
We don't want to compile code.
Well, let me just comment, right? What you can do is you can take small routines, and you can put them as C++ as the doc string of a function, and then that function is a C++ function, and you don't have to, and it just runs. So it could be that you could optimize some small number of functions with something like that. Just a thought.
And if we wanted to do that, we already have a working C code, right? That compiles with just an ANSI compiler. The point is,
right,
we want to keep the dependencies as minimal as possible so that this thing can actually work on the clusters. So PyBind 11 is unlikely to be there, and then linking that to a compiler. So we may consider doing something with compiled code if we have to. I think right now, the first step of optimizing this is going to figure out what data it actually needs. And right now it computes too much data and then get rid of it. The slow part is basically the post-Newtonian model contains an ODE that you need to solve. And that, of course, is much, much slower to do in Python than it was in C.
Bill Gabella has a question. He says, do I recall the double integration of Psi4 has to be done carefully?
Yes.
And you must be doing this as simulation tools handles this correctly.
So we're doing the double integral using a fixed frequency integration again. And the double integral is actually well understood because that's the same thing that you always had to do. It's a little bit trickier, say, to do the first integral that also appeared in Nakano's method because there you, in some sense, you only get one free parameter to choose. But it seems to work. But yeah, there is trickiness involved in these integrals that show up in these expressions.
We have a question from Atul. Atul, go ahead.
Hi, Roland. Can you just talk a little bit about what Scry+ is?
Oh,
that's my question.
So jargon here. So Scry+ stands for script I, and it's future null infinity. So it's basically the point where in space-time you actually observe gravitational waves.
Okay. I see. Thanks. Now it makes sense. Yeah, thanks.
We have another question from Dr. Peter Diener. Peter?
Yeah, so the Nakano method, as far as I understood, only need data from one radius in order to extrapolate to infinity, right?
Yes.
So I guess you can use different radii and then get an estimate of the error.
Yes.
Okay.
Well, yeah. So yeah, you get an estimate for one of the errors. Yes. Yeah. So it's complementary to the extrapolation method because it only needs one radius.
Okay. Thank you.
I see no other questions. Let's give virtual applause to Roland. Our next speaker is Yufeng Lua, who will talk about the data vault.